Alright class, today we're looking at our first pair of free response questions for AP Review. I'm going to be working these out with the scoring guidelines. If you're watching this video before you do these problems, you need to stop and go work the problems first. Then, just like we would do in class, I want you to give yourself a score based on how you do. Okay? So, do not watch the video first, do the worksheet first. Alright, so let's get started with this one. Let R be the shaded region bound by the graphs y equals square root of x and y equals negative, or e to the negative 3x, and the vertical line x equals 1, as shown in the figure above. Find the area of R. So this is our first part of this problem. We need to find what this area is. So we see that this area starts at whatever this intersection is, and then goes to 1. And based on what we know about these graphs, the upper function is the square root of x, and the lower function is e to the negative 3x. Okay? So, what we need is, if we want the area, we want the integral from a to b of our upper function, so square root of x, minus our lower function, e to the negative 3x dx. Okay? Alright, so let's look at this one. We know b is 1. How are we going to find a? Well, a is where these two equal. So where the square root of x equals e to the negative 3x. Now, this problem is a calculator problem. You should have seen that whenever you looked at the assignment in its learning. This problem is calculator. All right, so we would plug this into the calculator, and you should be able to get, we have a point of intersection at 0.2387, something like that, comma, 0.4886. Alright, so this is the x, this is the y. So this gives us our point of intersection. Now we get both of those because we don't know. We might need that y later. We might not. Who knows? But we definitely know we need the x. Okay, so we're going to plug in this x as our lower bound. I'll just call this equals a. That way we don't have to rewrite it. So the integral from a to 1 of square root of x minus e to the negative 3x. And then we plug it into the calculator, and we get our answer of 0.442. Okay? So for this part by itself, you'd get 1 point, or you get 1 point for the correct bounds as long as you do it once in the problem. All right? Now we're going to talk about what that means in a second, but essentially you're going to be using these bounds for all these problems. But you get 1 point for the correct bounds as long as you do it once. In this specific part, you get 1 point for the integrand, so 1 point for setting up this properly, and 1 point for your answer. Remember, the only reason I could use this equals a here is because I said that that equals a. If I didn't say this equals a, I wouldn't be able to do it. All right? Let's move to the next one. All right, so let me make sure I have this written. 1 point here, 1 point here, and then just 1 point in general for having the correct bounds. All right, let's move to the next part. Part B says, find the volume of the solid generated when R is revolved around the horizontal line y equals 1. So that's this line right here. We're revolving it there. Okay, so we're revolving vertically, which means we should be trying to use our disk and washer method. And remember, that has the integral, or 2 pi, times the not 2 pi, sorry, pi times the integral, pi times the integral from a to b of the outer function squared minus the inner function squared, or the inner radius, not inner function, because we're going to talk about that in a second. In this problem, we're using x, so we'll say dx. Okay, so let's look at what our outer is. Our outer is our outer radius. It's the distance from our axis of revolution to our furthest function. Well, we know this is going to be the function furthest away, right here. Right? So that's our function furthest away, right along this line. So our distance from here to there is going to be our axis of revolution, 1, minus that function. So e to the negative 3x. And then our inner is going to be the axis of revolution minus our inner function, or the closest function to it. Well, this now becomes the closest function to it. So that's 1 minus the square root of x. So when we set this up, we have pi times the integral from, in part A, we said a equals to that number, but let's say it again just to make sure. A equals 2.387, or sorry, not 2.387, 0.2387. Now, one thing I didn't note in the first part, since this is a calculator problem, ideally you would be just using the store function and storing this as a variable, so you're not having to type it out until we're exact. But we get from A to, and the end of our area is 1 of the outer, 1 minus e to the negative 3x squared, minus the inner, 1 minus the square root of x squared dx. And then from here, we just plug it into the calculator. Okay, so we plug it into the calculator and we get 1.423. Alrighty, there we go. Now, there are a few things for points here. Once again, let's say you use the wrong bounds in part A, but you use the correct bounds here. You'll get that point here. Okay? 2 points for the integrand. So that means 2 points for setting all this up properly. Right? So 2 points for setting all of this up properly. Now, there are a few things. You could get -1 if you reversed it. So if you did these in the wrong order, you could have gotten -1. If you would have gotten something wrong with the constant there. So -1 if the constant. Okay. If you completely left off the 1, you would have gotten -1. That's also there. For any other error, you would have gotten -2. So 2 points for that whole part right there. Then 1 point for this answer. Okay? So far we've had 2 points for the first part, 3 points for this part, and 1 point that could be gotten on any part. Right? We're saying we've already gotten this 1 point. So we've gotten 3 of our points, or 6 of our points. So that means we have 1 or 3 more points left. So that means part C, it's going to have to be 3 points. All right, this last one. The region of R is the base of a solid. These are the frustrating ones. For this solid, each cross section is perpendicular to the x-axis. So we have cross sections that are coming down this way. Okay, that's what we're looking at. And is a rectangle whose height is 5 times the base. Right, so that's a rectangle. Think of that coming out toward us in the screen. It's not a great way to show it, but the height is going to be 5 times the base. So let's redraw this rectangle here. So we have this rectangle, we have the base, and we have a height which is equal to 5 times the base. All right. Find the volume of this solid. So how do we find the area of a square? Well, it's just base times height. So we're doing the integral from A to B of base times height, dx. Now, here's the thing. We don't know the height, but we know it's 5 times the base. And we don't know the base yet, but we can find it. Remember, our rectangle goes from here down to there. That creates our base. Okay? Well, if the length of the base is just a distance here, what is the length from here to here at any given point of this area? Well, that length there, b, is equal to that upper function of square root of x minus our lower function, minus e to the negative 3x. So that means our height has to equal 5 times the square root of x minus e to the negative 3x. So when we plug this into our formula here, we're still using the same a, but let's write it again. A equals, let me get that number back. A equals 0.2387. Okay, so we're using the integral from a to b, so we're using the integral from a to 1 of b, which is the square root of x minus e to the negative 3x, times 5 times b, the square root of x minus e to the negative 3x dx. We could simplify this by multiplying those together and saying it's squared, but that's what we need to set up. And then lastly, we need to actually have the answer. So this is equal to 1.554 when we plug it in the calculator. All right, so once again, I said 3 points here. If you hadn't gotten the bounds right in any of the other problems, but then you got it right in this problem, you got that point. Okay. Now let's talk about the ones that are specific to this part. Once again, you get 2 points for setting up the integrand properly. So 2 points there. If you already set it up perfectly, you're fine. The only way you could have gotten 1 point instead of 2 is you would have gotten -1 if it's incorrect, but you somewhere used the square root of x minus e to the negative 3x. If it's incorrect, but you somewhere used that and multiplied it in, whether you made it the base or made it the height, then you would have gotten 1 point. Any other problem, you would have lost both. And then 1 point for the answer. So in total, 9 points. 3 points here. 3 points here. 2 points on part A, and then 1 point if in any of the parts you use the correct bounds. Okay? Alright, so that is the first of our 2 free response problems. So let's look at the second one. Alright, so let's look at the second one. Alright, so we have the function f is twice differentiable for x is greater than 0 with f of 1 equal to 15 and f double prime of 1 equal to 20. Values of f prime, the derivative of f, are given for the selected values of x in the table above. Alright, so what this is saying is we know f of 1 is 15, the second derivative at 1 is 20, and this table shows us some derivatives. Okay? So write the equation for the line tangent to the graph at x equals 1. Use this line to approximate 1.4. Well, that should be easy enough. What are the 3 things we need for a tangent line? Well, we need x. X, they said, was equal to, we're looking for the tangent line at x equals 1. We need a y. Y was given to us. F of 1 is equal to 15. And we need a derivative, or a slope. So we need f prime of 1. Well, that we can get from the table. 8. All right? So now we have that. We can create our tangent line. Y minus 15 equals 8 times x minus 1. All right? So then it says you use this line to approximate f of 1.4. So we know f of 1.4 is going to be approximately what we get when we plug in 1.4 there. 8 times 1.4 minus, 1.4 minus 1 plus 15. And then we solve this out. Now, this is not a calculator problem. You would not use a calculator for this one. You should have seen that in the It's Learning assignment. So we'd have to work it by hand, and we end up getting f of 1.4 is approximately 18.2. Okay? In this problem, you get 2 points for this. You get 1 point for the tangent line, and then 1 point for your answer. Okay? Let's move to part B. Use a midpoint Riemann sum with two subintervals of equal length and values from the table to approximate the integral from 1.4 or from 1 to 1.4. Use the approximation to estimate the value of f of 1.4. So let's start by doing just the approximation of the integral. We know a midpoint Riemann sum approximates the integral, so we know that the integral from 1 to 1.4 of f of x is going to be approximately the midpoint Riemann sum that we set up here. So it tells us that the midpoint Riemann sum with two subintervals of equal length. So we need two subintervals, and they have to be the same length. So 1 to 1.2 and 1.2 to 1.4. All right? And values from the table. Okay, so we're going to use these values. Now, let's think about what we're doing here. When we're doing a Riemann sum, we're summing up rectangles, which is base times height. So the base is the distance between the x's, and that's going to be the same no matter what. Our distance between the x for each of these is 1.2. Or sorry, not 1.2, just 0.2. 0.2, not 1.2. Okay, so we have 0.2 times, and then our heights, and these are going to be added together. Now, because it's midpoint, the height we're using is the middle value. So that means the height here is going to be 10, the height here is going to be 13. So we have 0.2 times 10 plus 13, and this is equal to 4.6. Now, that only answers that first part. We need to estimate the value of f of 1.4 using this. Well, that means we need to take into consideration what the starting value is. All this tells us is how much did the f function, how much did f of x change over this time? Okay, what's its displacement? We need the actual location of the point once it got to 1.4. And to do that, to approximate f of 1.4, that's not going to approximately equal. That's going to equal, f of 1, our initial value, plus that integral from 1 to 1.4 of f prime of x dx. Okay, that's how we're going to get 1.4, but because we approximated this value, that means we're also going to be approximating f of 1.4. So f of 1.4 is approximately f of 1, which was 15, plus this integral, which we approximated to equal 4.6. And so we end up getting f of 1.4 is approximately 19.6. There we go. All right, 3 points available for this part. 1 point for using the midpoint Riemann sum properly. So 1 point there. 1 point for using the fundamental theorem of calculus, which is this part here. That's part of the fundamental theorem of calculus. And then 1 point for your final answer. Okay? So there is our full answer and point distribution for part B. Let's move to part C. For part C, use Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 1.4. Show the computations that led to your answer. So remember, for Euler's method, the way it works is f of y1 equals, or sorry, not f of y1. Let's do it this way. So let me write it this way. y1 equals y0 plus delta x times f prime of x0. Okay? So what this is saying is to move to the next y value, you need the previous y value and the previous x value. So we're saying we want an Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 1.4. So that means x naught is equal to 1 and y naught is equal to where is it? 15. Okay? So to get our next x, we're going to add what our change in x is. Right? We need 2 steps of equal size, and we need to end up with 1.4 as our x. So to get 2 steps of equal size and end up with 1.4, we're going to add 0.2. And that is our delta x. And so x1 is going to be 1.2, and then x2 is going to be 1.4. All right, so we have delta x, that's that 0.2, and we have what we're looking for. So to get y1, we're going to do y naught, 15, plus delta x, which is 0.2, times our slope at our previous x value. Well, our slope at our previous x value was 8. Okay, so this says f of 1.2 is going to approximately be 15 plus 0.2 times 8. And that gives us 16.6. Now, this is also the same as saying y1, and that's going to help us to find y2. So y2, we need the previous y value, which was 16.6, plus our delta x, 0.2, times the derivative at the previous x value. So the derivative at x1. Well, the derivative at 1.2 was 12. All right, so now we say, okay, this is going to be approximately equal to f of 1.4. So this is approximately 19.0. Okay? And so this is our Euler's method approximation. You could also use the table that we had whenever we did Euler's method. I just thought this would be quicker since it's only 2 steps and we just needed to quickly add it. All right? You get 2 points for this one. 1 point for correctly setting up Euler's method with 2 steps. That's this part right here, making sure you use the right y's, the right x's, and the right slopes. And then 1 point for the correct answer. Now, your work, once again, does not have to look like mine. As long as you did Euler's method correctly with 2 steps, you're fine. Lastly, we're moving to part D. This should be the most recent, and so it should be easy enough to see. Use the Taylor polynomial to approximate, or use the second degree Taylor polynomial to approximate f about x equal to 1. So that means our center is 1. And then use it to approximate f of 1.4. All right, so let's first start with the Taylor polynomial. The second degree Taylor polynomial, well, that's f of c, f of our center, plus f prime of c times x, that's the first degree, plus f double prime of c times x squared, or sorry, not x, x minus c. Look at me, already forgetting things. This should be x minus c squared over 2. That's the second degree because we're on the second power. All right, so that tells us enough. So the 3 things we need here. We need c, which we said was 1. We need f of c, so f of 1. Well, they gave us that. That was 15. F prime of c, which is f prime of 1. They gave us that. That was 8. And f double prime of c, which is f double prime of 1. They gave us that. That thing that we haven't used at all this problem, it was specifically for this part. And we can plug them all in. So f of c was 15. plus f prime of c, which was 8 times x minus c, so x minus 1, plus f double prime of c, which is 20 times x minus 1 squared over 2. We could simplify that down by just saying this is 10 times x minus 1 squared. Okay? And so this is our approximation for f. And so we want to say, okay, f of 1.4 is going to be approximately what we get when we plug in 1.4. So 15 plus 8 times 1.4 minus 1 plus 10 times 1.4 minus 1 squared. Plug it all in. And once again, not a calculator, so you are going to have to do this by hand. We should end up getting 19.8. This one also had 2 points. 1 point for setting up the correct Taylor polynomial, and then 1 point for the correct answer. And what we notice if we look back through all of these parts, all of these were different ways to approximate f of 1.4. And with all of them, we got a pretty close approximation. I would argue that this would be our closest approximation, but all of them were kind of close. The other one that was really close was the integral that we set up. Okay? All right, so that's all the points for this one. 9 total points. 2 for this part, 2 for this part, 3 for this part, and then 2 for this part. Alrighty. So you've now seen both of these problems worked. You can give yourself a score and make sure when you submit it to me, you have that score on there. I need to see the score on there before or when you submit it. Okay? Y'all have a great day.